Hi there, Physics 152. I hope you're doing well. This week's practical is all about capacitors and measuring capacitance. I can tell you that this is a capacitor, two metal plates for which you can vary the distance. I can also tell you a little handful of capacitors which I picked up from my technologist. So these are all capacitors as well. So let's start by talking about what is a capacitor. So a capacitor is a device that stores electric charge when hooked up to a DC voltage. Capacitors also store energy. A capacitor is made up of two conducting surfaces separated by an insulator. So you place a positive electric charge Q on one of the conductors, and an equally negative charge minus Q is placed on the other, making the overall capacitor neutral. This creates an electric potential difference, or voltage, between the two conductors. So we can draw that. Sometimes we draw that as two lines. That's sort of the circuit diagram, but they could be sort of big plates or something like that. And then on this plate, we have a charge plus Q. And on this plate, we have a charge of minus Q. And the way you normally do that is you hook that up with a wire to like a battery. So we can draw a battery like that. And then this plate is hooked up to the negative terminal of the battery. And so this is a voltage V. And the capacitance of the capacitor is defined as C is equal to Q divided by V. And it's a positive number. The units of capacitance is defined as, it's called a farad, and that's equal to 1 coulomb per volt. If you want to know what some capacitors really look like, here's three. This is a 0.1 microfarad capacitor made of two metal plates that are actually rolled into a roll with an insulator in between them. This is another one of these roll type capacitors, 220 microfarads. It is actually possible to measure the capacitance using a capacitance meter, such as this one. It's called a capacitance meter. You turn it on, and it gives you the capacitance between these two sides. So if we take this 0.1 microfarad, you clip one on, doesn't matter which side, because these are, so right now I'm on 2,000 picofarads. The one with spaces after it means I've gone to infinity. I've gone over the limit. Let's turn this up, there we go. So when the maximum is 200 nanofarads, I've got, this is 101.2 nanofarads, which is, 0.1 microfarads. So that's good. Let's test out this other one. 220 farads. Oops, gone over that. This is microfarads. Turning it up, there we go. Oop, no. 2,000, yeah, so this is about well, there you go, 220 microfarads, just as advertised. This one, you may notice, is a very different order of magnitude. It is 0.47 farads. So this is what's called a supercapacitor. And it's sort of a new invention. It's made of some sort of material that has a fractal surface, which creates this huge effective surface area. So you can't even measure it using this capacitor meter, because this goes up to a maximum of 20 millifarads. But what you can do for fun is you can show that it is possible to use a capacitor kind of like a battery. So if I have a DC battery right here, and I plug it in, I can charge this up. And what I'm going to do is use this to try to light this light bulb. I'm going to put the light bulb right here. I'm going to have to turn off the lights in order to do this. All right, so we'll unplug this, and then this is just hooked to the capacitor. Let's plug it in. And then you see the light goes on, and it's only hooked up, no batteries involved, to a capacitor. See how long, oh, it's fading away already. So a capacitor, which is basically just two plates separated by an insulator, can be used as a way of storing charge. And so there's still a little bit of light there. So what we are going to be doing today is playing around with parallel plate capacitors. Basic idea with a parallel plate capacitor is when two parallel conducting plates of an area A are held a distance d apart and an insulator is placed between them, their capacitance can be found as C equals epsilon times A over D, where epsilon is the dielectric permittivity of the insulator. So you've got these two parallel plates. This is an area A, this is an area A, and you've got a distance D between them. Okay? And there's your capacitance. Now, when a vacuum separates these two plates, this equation, you put a little sub-zero, epsilon naught, and you get the permittivity of free space, which we know is 8.854 times 10 to the minus 12 farads per meter. So that's where your little epsilon naught comes from. It's called vacuum permittivity. So the first experiment is going to be measuring or trying to determine the permittivity of air between these two metal plates. So I've hooked up the capacitance meter to these two plates. I can see it's a 131 picofarads actually, so 10 times 10 to the minus 12 farads. And then I can measure the separation between these plates with these calipers. And if I do that very carefully, you can see I get about 1.8 millimeters. So I've already done this experiment, but 1.8 millimeters corresponds to 131 picofarads. Then if I increase the distance, I'll just hold this up. If I increase the spacing between the plates, and you can see that the capacitance drops down to about 89 roughly when I measured 2.7 millimeters. As we get farther and farther out, I'm going to go just about as, out to around 9 millimeters. So I've already entered this into the Google spreadsheet, a list of separation distances in millimeters versus the capacitance in picofarads between these two plates. So your job is to try to do a fit to that and try to make a determination. One more thing you're going to need, of course, is, let's disconnect this, you're going to need the diameter of the plates. So the way I did that, I already put it in there, is I just grabbed a ruler and measured centimeters diameter right across the center there, 17.7. Almost exactly 17.7, so like a uncertainty, maybe half a millimeter there. So the next experiment, for experiment 2, I actually want to measure the permittivity of the paper in this textbook, this sort of glossy paper, which has the nice property that it's got a pretty even thickness. So I'm going to use these plates now, since they can be kind of sandwiched in this textbook. First thing we'll do actually this time is measure what the area is. So these are square plates. Let's just check that. I've got 15.2 centimeters by, plus or minus 0.05 centimeters, and then 15.2. So they are square, and they have side length 15.2 centimeters. What I'm going to do is take 5 pages. I'm going to put one there and 5 sheets. So we're on page 725. 1, 2, 3, 4, 5. So let's just start with 5, and we'll put the second metal plate right there, and we'll close it. We have a little bit sticking out, but make sure they don't actually touch each other. And then we're going to smush them into the book again, so they're not touching. Now I'm going to turn this on, and I'll hook up black to the bottom one, just where it's sticking out. very carefully, and red to the top one. Again, just where it's sticking out. Oops, that's more than 200 picofarads. It's in picofarads. 1391 picofarads for 5 pages. So next, I'm going to put more pages. Let's turn this off for a second. So now I've crammed 10 pages there. 10 pages, about 854. Okay, from page 725 to page 815. That is going to be 45 pages of this textbook. This will be the last measurement that I make. Again, cram them together. Notice they're not going to be exactly overlapping, so I should probably reduce my effective area of this by just a little bit. Clip black on there, red on there. Okay, so for 45 pages, I got 233 picofarads. Okay. Next thing we need to know is how many pages, like what's the thickness of a page, right? So the way I'm going to do that, I'm going to take the entire textbook, 1 to page 1240. So 1240, where each side is numbered twice. I've got 36.4 millimeters. 36.4 millimeters, and that is for pages 1 through 1240. So since each piece of paper has 2 numbers on it, we want to divide it by 2. So 36.4 millimeters is 620 of the pages. So then we can find how many millimeters is 1 page, and then we can convert those distance measurements or page numbers to distance measurements of separation. So you'll find all the data on the Google spreadsheets. You may want to make a copy of the sheets so that you can use Google Sheets with an equals formula to compute your own numbers. For example, I've only typed in the number of pages or number of sheets of paper between the 2 plates, but you will need to convert that to a separation in meters. So you can make another column and reference those numbers to compute the separation. Then you want to do some fits, and remember what you're after is the permittivity. Could be the permittivity of air or of paper, and you can also compute kappa, which is the relative permittivity compared to vacuum permittivity. So have fun and good luck.